This is a subwoofer that might be in the back of a very noisy car, or it could be in a concert venue, or maybe in your lounge room. A subwoofer has a big speaker in usually some carefully sized box, and may or may not have a port here as well. So I thought this might be an interesting example for a number of different things in parametric design and other parts of Onshape. Show off a couple of renderings here first. These were all done in Render Studio. So let's start at the beginning. And the beginning is the top. This is a top-down design example where the overall length, depth, and height of the box, as well as a couple of other key things like the diameter of the speaker, 10-inch speaker, the thickness of the MDF wood, 19 millimeters. These are all very high-level global variables that I'm going to use in many different places. So I've used a variable studio. A variable studio is something you can create yourself here in any document. In fact, the variable studio can exist in its own document and therefore be version controlled and linked to other things, other documents. But in my case, I'm going to put the variable studio first here, define these numbers, and then start using them in other places. And I'm going to roll through this rather than try and build this again from scratch, because it probably take a little time. Anyway, so typically I would start with a skeleton, and a skeleton might be as simple as a box like this. And I've made it translucent so that we can know that it's a skeleton. The skeleton profile, the sketch for it, is of course driven by the depth and length variables, and the extrude depth is driven by the height variable. Those variables are not defined in this individual part studio. They are coming from the variable studio, which is the global variables. If we pull open the variable panel here, the variable table, you'll see a listing of two tables. There's the stuff that's come from the variable studio, and there's the stuff that's local to this enclosure. We've got no local variables here at the moment. You can use these variables, length, depth, and height, like I have. You can see them being highlighted, cross-highlighted. It's interesting and very powerful that to see the height variable from the variable studio is being used in the skeleton extrude as the cross-highlight. So that's useful and very cool, because I can obviously change these things on the fly just through the panel here. I then created a bunch of panels using those faces as references, and then the thickness of the panels that I created was based again on the thickness variable. I just hash thickness refers to the thickness variable that was over here at the high level, at the top level. So I've got my panels, I've cut my speaker hole, and now I'm going to cut the fastener holes. So the fastener holes are the fun bit here. So what I did is I created a sketch here, which is a line where I'm going to line up, that's this sketch here, where I'm going to line up the holes. Now I drilled one hole, which is a countersunk clearance hole here, that goes through two parts. If I highlight the conical section there and cut a cross section, you'll see where that hole goes. Just for those that couldn't see my keyboard, which is everybody, I'm using the tilde or tick key to cycle through in the select other. It's a handy one to use. Otherwise, you can actually right-click and choose select other as well, and it'll give you a list down here. So the face of the hole, any conical or cylindrical or planar face you can use to create a cross section, and then maybe make one of them like that. Anyhow, so that's the first hole. I then created a measurement, a variable from a measurement. So what I did is I measured the length of this line, the sketch that I had created. I measured it and said the result will be this variable called length hole pattern. All right. So now it gives me 481 millimeters. And now I'm going to pattern that hole along this curve. So I've chosen the hole as a feature pattern. I've chosen that curve as you're going to go along it. Now if you know the curve pattern in Onshape, you know that you have that feature will be at the first, there'll be one of the same feature at the last, and then the number of instances is set by this thing here. Now I've used an expression which is this one here. You can see it here. I've taken the length of the whole pattern divided by the fastener pitch, which is another variable, so that's the pitch between them, and I've rounded that off and then added 1, right? So that's an expression that I've just written in line, so that'll give me a number. It's not going to give me a fraction or anything like that. It'll give me a whole number plus 1. So it's going to drop me 11 instances in here, and then I'm going to do a couple of mirrors and do the same thing a couple more times as I go around. You know, I've mirrored it here, I've mirrored it here, I've done another one of these patterns, mirroring them, and I do it another time to get all of these ones on the front and the back and underneath. So now I've got my whole set of fasteners ready. I'm going to create a cut for the port. I might turn the skeleton off, it's bleeding through the graphics. You can see it's bleeding through. There you go. The port is a hole which is cut through here, and I'm going to run a simple pattern of holes ready for the fasteners. In this case, it's just a simple circular pattern. Now, there are a couple of rules that I can check. Now, there's kind of a rule of thumb or tradition or empirical rule that says that the distance between the edge of this port and the face or the wall has to be not less than the diameter of this hole. So I have done a measurement here which says let's measure the distance between, you can see the purple line there, it's measuring the closest distance between that edge and that edge. So it's giving me, and I've said Z check. Done the same thing with the Y direction. There it is. And then I've written an expression here, which is an interesting logic inline, which says, I'll go over to the variable table to have a look at it a little bit better. So the Z check is going to be equal to, if a Z check is less than the port diameter, then the answer is no good. Otherwise, the answer is okay. So it returns a string here. You can do this kind of gross or simple hack for a little design check inline. So of course we've got ours is returning a value of okay. There's another feature that is a custom feature called a sensor, and I will unsuppress this one. And the sensor is just is a little bit more sophisticated in that we can measure a distance. Again, I'm measuring the distance between this entity and this entity, and the warning will be if it's less than 70 millimeters. You can set the warning as less than equal, greater than equal, or greater than, and set the value in. So it's a minimum distance. It's less than 70, then we get a warning. And if you have a look in the custom tables, there's a thing called sensor values, which will list all of the sensors you've got. In fact, there's another one. I can make this a little bit more interesting. We've got 2 of them. There's no warning. If there's a warning, if there's the distance is not, if it's less than 70, then this will be highlighted in red, and the feature will actually show in a failed state. So that's a way that you can eyeball it down. You can see that if your sensors are failing to regenerate, then you know that you need to fix something. Yeah. So that's a couple of different ways. You know, if you're just doing a quick one, I don't mind using this, even a misspelled version of an offset, as a way to do it quickly. Oops, there we go. So now, continuing on, let's go to the end. I'm I just cut a little relief out here, a counterbore, so the speaker can sit down in there a little bit more carefully. So now that's the enclosure done. Let's put it together. So I'm using, there's a speaker that is coming from a different part studio. Let's not worry about that now. Fasteners, right, so fasteners I have, okay. I also put the port tube in here. Right. Now when I've used fasteners, I have, where's the first one in this little group? Yeah, okay, so I just put a fastener from a standard content, and I used a replicate to do everything else. So all those replicates, and the same thing with the replicate that I did around here. I put one fastener in and replicated using a part, and if you have a look at the definition of it, it says parts to find the match in. So if you select carefully when you insert the first standard content instance, if you select carefully on the part, you'll get the ability to just match to similar entities like these. And in this case, it's usually the safest one is to use the flat face, flat sort of annular face at the bottom of that countersunk hole. Same thing over here, careful use of that. Now, the beauty of that, it means it remains parametric. So a parametric replicate is really what that should have been called, and in fact, that's what we do call it. So to show that, I can go back to the variable studios, numbers. Now I can do it through here and change the pitch value, but it's more interesting that if I do it here, it's just the same thing, right? So if I change this to 25, and 25 millimeters of fastener pitch, I'm going to throw a whole lot more fasteners here. I definitely don't want this thing to fly apart under the huge sound pressure that I'm giving it. So I've changed the fastener pitch. This obviously affected the holes. This is because this is how we defined the pitch of the holes. And the fasteners themselves have updated correctly to do that as well. So let's undo that. And we get back to our more modestly connected, and I think it's going to be just fine like this. Now, just as one final bonus, I am interested in calculating the resonant frequency of this, because this is kind of what it's all about. You want the resonant frequency of this box, the air in the box, to be around 32 hertz. Perhaps that's a goal typically for an automotive subwoofer of this 10-inch kind of size. So how would you do that? Well, what I did is I created a part studio in context, or an in-context part studio. I always call them ICPSs, just so that I remember. And what I did is I extracted, and if I show the context, you'll see what I mean. The green bit is all of the air, the space that's in the air, that's enclosed by this box. So what I did is let's see if I move this back. So I created an air volume kind of like this, but it's just by using the inside offset surfaces, right? And I filled a couple of holes in, created this, and once I had this, I extracted the space that the speaker would be leaving there. So that gives me this this enclosed space. Now I'll turn this back off again because I've kind of given the game away, but I have a custom feature that I created, and if I turn the context off, it might be clearer. Yeah, that's better. I created a custom feature which is called HELMHOLTZ, because HELMHOLTZ resonance is the principle we're going for here. And it allows me to define an air volume, or even just select an air volume. So in this case, we know this is the air volume. We're going to select it. And there's a port, and the port is where the air is allowed to come out. So this is the face of it. And the side face, I'm going to use this select other, And the feature, well, firstly makes the air volume translucent handily, and it then tells you immediately what the resonant frequency is. It happens to be 32 hertz because I did design this correctly. It allows me also to input the acoustic power of the speaker and the speed of sound in air, which is usually 344 meters per second. I can do some overrides if I really want to, but this is pretty close. And if I want to, I could go back and start fiddling with these global variables, maybe the length and width or the port length. That might be something interesting to do. So if I change the port length to something much shorter, like 100 millimeters, it's going to regenerate a lot of stuff. And it's also going to tell me that the context is out of date. See that blue dot there means that the context is out of date. So what I'll need to do is update the context, and after I've updated the context, it's going to regenerate all of this, which includes recalculating the resonant frequency. So let's do that. Let's update the context now, and with any luck, this should be finishing now. And see, now the resonant frequency is 42.5 hertz, too high. And that's typical if you have a port that's not long enough in a subwoofer. So let's go back to 208. And again, it takes a second, and then it'll tell you that the context is out of date. This is kind of new. New as in within the last 10 releases of Onshape, but that's only 6 months. So, sometimes it's hard for people to keep up, especially if you're used to yearly or longer release cycles. 3 weeks is pretty fast for in Onshape's case. So let's update the context and get back to where we wanted to, which is the 32 hertz in here. Now there's a little bit of a bonus down the bottom here. I've been calculating this. There's some debug options and some things that, from my custom feature, I'm actually calculating the peak airspeed through this port, and you don't want this to be more than 10% of the speed of sound. So it's a quick check in here, that 19.5 meters per second, we're still good. If you have a port too small, the diameter is too small, then you tend to have high airspeeds, and you can start to hear some sort of chuffing sounds, which is also not desirable. So that's a quick tour through this model. There's a lot, I guess, covered and to take in here. Really, this was examples of top-down design, parametric designs. There's some custom features in there, parametric replicate, all sorts of things that really show off, some of the real superpowers of Onshape.